Welcome back. Part 4 of the series is a relatively simple example demonstrating Hooke's law. We'll increase the complexity a little bit by giving a problem statement that we have to read and interpret to extract the meaningful information for the problem. This example is from Mechanics of Materials by Timothy Philpott, Wiley, 3rd edition. Let's read the problem statement. A 0.75-inch thick rectangular alloy bar is subjected to a tensile load P by pins at A and B as shown. The width of the bar is W equals 3 inches. Strain gauges bonded to the specimen measure the following strains in the longitudinal, that's along the length, and transverse directions. Epsilon x equals 840 microstrains and epsilon y negative 250 microstrains. We are to Part A, determine Poisson's ratio, and Part B, if the measured strains were produced by an axial load of P equals 32 kips, what is the modulus of elasticity for the specimen? Okay, we have a relatively good picture here. Let's go ahead and summarize the given information for the problem. Given. Okay. What we know, we're given the strains. Epsilon x equals 840 microstrains. And we should point out that a microstrain is 10 to the minus 6th. So this is equal to 840 times 10 to the minus 6th, a relatively small quantity and unitless as expected. Epsilon y, similarly, negative 250 microstrains, or negative 250 times 10 to the negative 6th. Okay, we are also given the dimensions so that we can calculate the cross-sectional area. We don't need to know the length for this problem. If we draw a little picture, given the cross-sectional area, we might label this dimension as W and the thickness as T, and we are given that W equals 3 inches, and we were given that it's 0.75 inches thick, so we'll say T equals 0.75 inches. And finally, we were given an axial load of 32 kips. Okay, now let's summarize what we need to find. We want to find for Part A Poisson's ratio, which is unitless. And we want to find for Part B the modulus of elasticity. Worth noting before we even start the problem that the modulus of elasticity has the same units as stress, and if we are working in English units, we typically like to express stress in kips per square inch, or I like the shorthand KSI. Okay, so that will give us what we need for a unit check. Let's start with Part A. Poisson's ratio, by definition, is equal to the negative of the transverse strain divided by the longitudinal strain, both given in this problem. Very simple calculation. The negative of negative 250 microstrains divided by 840 microstrains, which is 0.298. Okay, and as a simple check on Poisson's ratio tends to vary from 0 to 0.5, where typical materials have Poisson's ratio in the range of 0.2 to 0.3. So this is a very reasonable answer. Part B, applying Hooke's law, which says that sigma equals E times epsilon. We're applying it in the x direction. We can solve for E equal to sigma x over epsilon x, where sigma x, the definition of stress, can be calculated as P divided by the cross-sectional area divided by epsilon x. P was given as 32 kips. The cross-sectional area can be calculated from W times T, 3 inches times 0.75 inches. and the whole thing divided by epsilon x, which I will write out as 840 times 10 to the minus 6th. Plugging all that into our calculator, we would get E equals about 16,900. I'm only going to carry the first 3 digits. Don't want to express the answer in too many significant digits. I wrote the units as KSI. Let's do a check here. Kips divided by inches squares, so it checks out.